Thanks for the invite to speak in this popular forum. So before I get started, I just want to mention I've been working with DynoChem on and off for the past 5 years, and over that period I've really seen it transform into an incredibly useful resource, not only through expansion of different model templates, but also new utilities being released on the website, and also just the really extensive selection of knowledge pages which give a great introduction to a really broad range of engineering topics. So if you haven't checked out the website recently, I urge you all to maybe after this presentation just go along and see what's been added. It continually gets updated, so it's a really useful tool. So today I plan to talk about some of the scale-up work I conducted for a project where we had a genotoxic starting material that was used in a biphasic reaction. And this was a particular concern to the project because as it was a known genotoxin, it became a critical quality attribute for the stage, and we wanted to make sure we had full control over the residual starting materials in that stage. So the first half of the presentation will cover looking at the kinetics and the transport of this biphasic system. This can be consumed by two major reactions: the main reaction, where it reacts with the starting material A, and also in the side reaction, where it reacts with D. Now, D is an impurity that we can have up to 10 weight% in A, and we wanted to ensure that, with the variation potentially of this impurity, we wanted to ensure that we could, the reaction rates for both reactions were similar, so that we could confidently say B would be consumed during the reaction time, regardless of the concentrations of that impurity. What we did is we focused on the simple hydrolysis reaction first, which was the consumption of B to give F. We were able to get this time course data. So the points you see are experimental data, and then the lines we fitted in DynoChem. So we fitted this across 3 different temperatures, and then we did the same thing for the main reaction and also the side reaction using different inputs. So and monitored that over 3 different temperatures, and you can see the fit is fairly reasonable for all the data we generated. We do start to see some excursions from the fit when you look at the side reaction, because we were looking at a range of vessel geometries and some really bespoke impellers. We decided to take the route of subjectively obtaining the NJD values in 2-liter minutes and then scaling up based on the power per unit volume. And just to give you an idea, the dispersed volume we're looking at is 10% of the total volume. So this really fits in with the low power per unit volumes that we were observing. So I put this chart in. It actually caused quite a bit of controversy when I presented it to the different plants. So what we see here, but I'll take you through it and explain it. But what you see here is basically how the power per unit volume changes with RPM at the different pilot plants and manufacturing plants we were looking at. And quite rightly so, engineers get very defensive of their vessels, particularly if you're highlighting one as being a worse performer compared to other plants. But what we see here is in the box on the left is the power per unit volumes that we predicted for the various geometries at small scale that would give you a just dispersed system. So these are really low agitation rates, and I would never, I wouldn't advise our plants running that low. So, we know that there's no risk of over-agitating this this reaction mixture. The exotherm that we saw is very mild. So if you do absolutely blitz it, you're not going to see a huge jump in temperature. So this is what we calculated, and actually the standard operating kind of mixing RPM rates are highlighted here, and you see even in the worst case scenario, the power per unit volume that we see at large scale is still 10 times what we need to get a just dispersed system. Used the Kinetic study to support a reaction time of no less than 1 hour, and in combination with the mixing study, it gave us confidence to achieve the maximum consumption of the starting material across the design space, and allowed the position of not filing a mixing related CPP. So gave ultimate flexibility for the plant to be able to move into new vessels without having quite an intensive validation process to go through.